How you doing, Dr. Hernandez? Hello, TCF. How you guys doing?
Very good.
Um, let's see. Let me get to the okay from the beginning. How is that? Good. So today I'm going to talk to you guys about my senior project. I'm working on a switch capacitor, KHN biquadratic bandpass filter. Fancy way of saying tunable bandpass filter, state variable filter. And just to preface, I know in the past we've used students have had posters ready to go in person. This is outdated. Um, it's a couple months old, but I have it ready upon request. But I figured easiest way, old reliable is PowerPoint. So today I'm just going to talk to you guys about project background, theory, project choice, like what is this project, like the components of it. I'm going to talk to you guys about project goals, specifications, hardware goals, printed circuit board goals, and maybe audio output goals. That's kind of like a reach goal, but I'll get to that towards the end. My current project standing, which I'll talk about, project work to date, like past work, and then how I stand as is, and then future project tasks, which I'll talk about, some of the filter hardware implementation, the switch capacitor hardware implementation, and then the printed circuit board. And then I'll talk about some current issues I have, some pitfalls that I might come across or have come across, hurdles to consider, hardware choices, and then analog versus digital, which I'll touch on just a little bit, because this is going to be a sort of bare bones presentation, given we only have about 15 minutes. And then I'll end it all with a conclusion and some practical applications of the filter and how it can be used in practice. So just to get started on project background, I'll talk about what KHN means. It's the Kerwin-Huelsman-Newcomb filter, basically, based upon who discovered it. It uses 3 op amps. I'm just going to call that the KHN from now on. It uses 3 op amps to simultaneously output high pass, band pass, or low pass filtering, all based upon one single input. So if you see here, op amp 1, if you take the signal output here, you can get a high pass result. If you take op amp 2, take the signal there, you can get a band pass result. And if you take the signal here, op amp 3, you can get a low pass. And for my project, I focused specifically on bandpass. And now you're going to ask like where the switch capacitor comes into play and what it does. This was new to me, the switch capacitor. We might have briefly touched on it in the past, but all this research was new to me. And what the switch capacitor does, it functions, basically as a resistor. It's a simulated resistor. And so with a resistor, you have a voltage, across that resistor that produces current. And what the simulated switch capacitor does is it takes 2 switches and will alternate them using non-overlapping clock signals, which basically means alternating clock signals. And what the switches do is it'll take, if you picture my head as the capacitor, and it'll alternate the switches to charge this capacitor up, which will result in an average current equal to that of a resistor. And you're going to ask, why? Why would you, what's the point of using a switch capacitor? Why wouldn't you just use a regular resistor? And the point is that resistors, once you get into, I believe like the mega ohm, like higher value resistors, they take up a lot of space and they're very costly to implement because they can't be accurate. And they take up a lot of space. So the switch capacitor, it can be tunable and it will take up less space than your average resistor. And I'll talk about a little bit at the end how they do have black boxes of where black box, I mean, it's just a switch capacitor chip that comes as is. But my project will be sort of a stripped down version of that, where I'll be building it from scratch. And so my goals here are to take this KHN filter design, which has the resistors initially, and replace all those resistors with the switch capacitors. And then that'll be, implemented so that it will be tunable and it will be able to be changeable using a clock frequency and pulse generator, which controls the switches of each switch capacitor. And then my third goals can't have a design goal without specifications. Again, I said I'm going to look at the bandpass filter specifically. I set for a center frequency of 2 kilohertz, a 3 dB bandwidth of 50 hertz, a center frequency gain of 80, and I want to generate multiple responses with the hardware and a fully functional hardware, which includes breadboard diagrams, breadboard circuitry, and then PCB. So to date, I have the KHN SPICE circuit completed. And you see I have obviously red square, blue square, green square, and that's all the outputs that you can have with the result of one input signal. Here we have the filter transient response, which shows the bandpass filtering application with the green single input. Then we have the filter frequency response, which shows it's centered over 2 kilohertz. And then I also have shown the center frequency gain, which is showing about 80 with, again, over 2 kilohertz. And so this is just laying the groundwork to show that the KHN filter works as is, pre-switch capacitor. So now my next step was to get the switch capacitor working in SPICE. And you can see here I have a 5-volt and a 1-volt battery powering the circuits. I have 2 transistors, N break N, basic breakout SPICE transistors with a 1,000 picofarad capacitor or 1 nanofarad. And what powers these transistors to switch alternatingly, like back and forth, is V3 and V4 here, which function as pulse generators, which function as clocks. And we see on the left, we'll take a look at the left one. V1 starts at 0 and then steps up to 5 volts at V2 with no time delay and a time to rise of 0.1 microseconds and a time to fall of 0.1 microseconds. A pulse width of 5 microseconds, and then the PER, which is the it'll repeat every 20 microseconds. And if you contrast to the second one, this is how you get the alternating clocks. If you notice TD, time delay, that's a time delay of 10 microseconds. So that'll delay 10 microseconds from the first pulse generator. And that is how you get the switching function of the capacitor, which charges it up and gets the average current. So now this is just showing the transient response. This shows this green here, this green pulse generator at the bottom is my first pulse generator. And then this red rectangle pulse generation is my other one, which powers the other transistor. And you can see that they're non-overlapping, they are alternating. And then the 2 in the middle, the green, is the current generated, negative 200 microamps. And then this was a little below 200 microamps, but it still generated a current. And that results in an average current, which you take over time, resulting in around 40 microamps of current across that capacitor. And so that led me now to hardware design. And so with the hardware design, I had to find a MOSFET, a chip, a CMOS, to act as my switches. I found the CD4053B, which is a multiplexer, single pole, double throw, as you can see on the bottom here. It is triple analog, I believe, which means it has 3 potentials here, where it's like A, B, or C switches. And on the right, we see the pin setup, 1 to 16. And on the left is the pin functions. I'll talk a little bit more about this chip later and why I chose it and why I might use a different one. But for now, I'm using this one. 1 and 2 are the B channel X and Y inputs for one switch. 3 and 4, you'll see I'll have these grounded because I'm only using the A and B switches to power one single capacitor. And then those will be grounded. And then pin 6 disables all the channels. So I have that grounded so that all the channels are enabled or closed, these switches here. And 9, 10, 11, I didn't focus on. And then 12, 13, 14, 15, 16, I did use. These are for input, output to power the switches. So that would be where I would put the pulse generator, the clock to control the switches. Here I just have a little, I haven't tested this yet, but it's a little breadboard circuit of the switch capacitor. Here I have it labeled CD4053B just for ease of, ease on the eyes. The pin setup 1, 2, 3, 4, 5, 6, 7, 8, following, snaking to 9 to 16. And you have these black on the bottom or wires that I mentioned before that I have grounded, these pin inputs, such as, the ground for the chip, and then the C switch, where I have grounded because I'm not using. And then I have here VDD, which is pin 16, is the positive power supply to the chip. Pin 7 is VEE, which is the negative power supply for the chip. V out here, which will be the oscilloscope read to determine if the switch capacitor is working. And then AWG1 and AWG2 are the analog waveform generators, and AWG1 will power switch B, which will alternate switch B on and off, and AWG2, waveform generator 2, will be switch A's on and off clock, if you will, or power generator. So then that's where I stand currently. Future project tasks, I have all these resistors in the circuit circled because every one of these resistors I will be replacing with the switch capacitor resistor diagram and implementing that into hardware design. So that'll be done in the next month and a half. And in order to do that, I have to order the op amps. I'm considering an LM324 or an LM4562. Those are two op amps I've had experience with in the past. I have to do a little more research into those to decide which one I want to get. And then finally, the final design is the PCB circuit board design using either Easy EDA, Autodesk Eagle, or Circuit Maker. And that's the main implementation of the switch capacitor. The best value is with digital design rather than analog, from my understanding. And it's best with digital design, such as integrated circuits. Some current issues I have. I have to test the switch capacitor to make sure its function is correct, which at the end I'll talk about this chip. And then I have to decide whether I want to use analog waveform pulse generator as a clock. I've seen some instructors or testers use logic-based clocks using gates. You can also use the Arduino. I have an Arduino here that I can use to create a digital pulse clock. And that might be useful with the current chip I have, because the current chip is mostly used for digital. And that might be a little more useful. But currently, my current plan is to use analog waveform pulse generators just to get it working. And then some conclusion and practical applications. So the KHN filter is not trivial in a sense, but it's more simple. And then the switch capacitor resistor adds a nice wrinkle to make it a more complex function. And like I said before, these switch capacitor black boxes do exist now, where it's all in one. It's just a switch capacitor chip. But this project is more, we're breaking it down to understand each component and how it works. So I'll be building it, from scratch. And these switch capacitor filters are very applicable in audio signal processing, sound recording, and analog synthesizers. Like I said before, audio output would be a great goal. I saw one researcher, he was able to build a switch capacitor filter that was able to tune, and as he changed the clock frequency, he was able to output different audio, which was pretty cool. But other than that, that's where I stand at the moment, and I'm open to any questions or concerns or tips, and thank you very much.
Dan, I just have a comment. If you go back to your switch capacitor circuit or diagram,
The spice or the?
It doesn't matter. Doesn't matter.
Yeah, I wasn't too. I'm a little concerned about the circuit because I haven't.
Go back to like the spice or your original diagram with the switches. It doesn't really matter. So right there. So an enhancement to that topology is that, and you may run into some accuracy issues when you actually build it, because you can never remove all the charge from that capacitor. So you really, and that translates into is if you had a parasitic capacitor or a fringe capacitor across it that adds to it. So an enhancement to that topology is if you put the capacitor between those transistors, okay? And then you put another 2 transistors from those nodes to ground, and you control them. So imagine an M1 on the right of the capacitor, and an M2 on the left. So when you close M3, you will close the one that is on the other node on that on the drain of M4. And that way you can have actually a true ground, and you can actually ground both sides of the capacitor at the same time and discharge it. And that will actually translate into a better accuracy.
So would that be kind of like a double throw? Would that be kind of like a double throw?
That would be a double pole.
Double pole. Okay.
Double throw. Okay. Where you would actually control, like I said, an M3, and then an M1 that is tied to the drain of M4, and then you would control M4 and an M2 that is tied to the drain of M3. Okay. And those transistors will go to ground, but the capacitor would be between M3 and M4.
Right. Okay. And, yeah. Thank you.
Yeah. So that actually allows you to discharge the capacitor completely, and translates into
a better current. Yeah. A better current output. Yeah.
Okay. So you don't have an offset, because with this you will have an offset. I mean, in SPICE you can discharge it, but in real life you're going to have some type of offset, which translates to an error in the resistance, because the equivalent resistance is the capacitor over the period.
Right. Okay.
That's all my comment.
Thank you.
Any other questions or comments? Nice project.
All right. Thank you, Dr. Hernandez.